This is lecture 2 of single agent search, and in this part of the lecture we're going to break this into several different pieces. In the first part of this lecture we're going to look at search on trees, in particular trees that grow exponentially. And so we have some initial assumptions, and we're going to make these in sort of a very broad way. They don't universally hold. Later on in the class we'll look at how we can get some of these to be closer to working in practice. But we're some assumptions here and some notation. So we're going to have C star is going to be the optimal solution cost. And we're going to assume that there is a single goal state. We're going to assume that we have that all edge costs are uniform. So we're going to assume, for simplicity, that they all have cost 1. We're going to assume that there is a branching factor of B. And we're going to assume that the solution depth, or in this case the solution cost, it works the same way. So it's going to be D. And so, of course, for the simple case, this is going to be the same as C star. So this here describes an exponentially growing tree. So that's because of the branching factor being constant and going to some depth. If I had a polynomial state space, just as a point of comparison, then we would see at radius, so if I search to some radius r, then I would see r to the d states, where d is the dimension of the state space. And so here the dimension is constant. And so like r squared states or something like that. But we're going to look at an exponentially growing tree, and we're going to see what happens and what are the properties of an exponentially growing tree. And so there's some things that we're going to look at with different algorithms. We're going to repeat this again and again. And so it's important to understand these metrics, because we're going to evaluate each of the algorithms we look at according to these metrics. So the first thing we want to look at is if an algorithm is complete. And complete says that if a solution exists, then we will find it. And so this is like a suboptimal algorithm. It finds a suboptimal solution, could still be complete. That is, if a solution exists, it's guaranteed to find it. We can be optimal, which means it's always will find the shortest solution, or the lowest cost. If we're not optimal, we could look at the solution quality and ask questions about that. And then we want to talk about the time that it takes to run the algorithm and the space that it takes. Time is generally going to be measured in nodes, or this related to this would be node expansions. That is, how many times do we look at a state and generate its successors? And this space complexity is also in nodes, but it's the number of nodes that are stored as part of the search. So we're going to keep these metrics in mind. We'll come back to them again for each of the algorithms, and even later in the class we'll be looking at these. Okay, and now the question is, when we look at a tree that grows exponentially, how many nodes are there in the tree? And just to give an idea, we can look at this. So this is an example tree here that we have. And so this is a tree. If we look at this, it has a branching factor of 3. And it has a depth, if we think at the top, we can count our way down, a depth of 1, 2, 3, 4, 5. Okay, and we see here, it's pretty clear that the number of nodes, I can see very clearly the nodes at the first level, but the nodes at the bottom level, there's quite a few there. It's very difficult to count or to see how many are there. So we want to come up with a general way of counting how many nodes there are in the tree, and then we want to look at the properties of the number of nodes that there are. Okay, so let's take a look at this. And what we're going to do is, so this is our sort of our background for this lecture. And we're going to start out by trying to write down an equation that says how many nodes are there in an exponential tree So, and we'll call this a function n. It's going to be a function of the branching factor and the depth. Okay, and if we go back, in fact, and we think about the tree that we were looking at here, so if we look at this, what we see is at the very top level, there's what we see in this tree, the branching factor is 3. We see 1 node, and then the next level, there's 3 nodes. And then each of those 3 nodes become 3 more, so then there's 9 nodes. And so again, going back to our slides here, what we're going to see is this is 1 plus b nodes. And the next level, we see there's b squared, and then there's b cubed, and then there's b to the d. So b to the d nodes is going to be how many we have at the last layer, but of course there's a bunch of layers that are going in between here. And maybe you've seen this before for a fixed branching factor, but we want to understand what happens in general. And the way we're going to do this is fairly simple derivation here. And I'll just write this here. So we're going to multiply both sides by b. So I'm going to have a factor of b on this side. So b times n of b comma d is equal to, and then here again, I'm going to put a factor of b on this side. 1 plus b squared. Okay. And then just to write this out again one more time, we get b times n of b comma d is going to be equal to b plus b squared plus b cubed plus b to the d plus 1. Okay. And now what we have here is we have 2 different equations. So we're going to look at this equation here and this equation here. And what we can do is we can subtract these 2 from each other. And if we subtract, so if I call this line 3 and this is line 1, what I want to compute is 3 minus 1. And what that gives me is b minus 1 times n of b comma d. And that's equal to, and then what we notice here is that along this equation here, all of the values inside here are the same as all the values here. And the only thing that's going to be left is 1 term on the end and 1 term on the end. Okay, so if we do this, we get b to the d plus 1 minus 1. Okay, and now we can do a fairly simple just a little bit more algebra here. N of b comma d is going to be equal to b to the d plus 1 minus 1 over b minus 1. And what we notice here is, again, we can say this is equal to, I'm going to take a b. So we're going to take this term right here of d plus 1. We're going to take one of the b's out of there. So we're going to get b times b to the d minus 1 over b minus 1. And what we get here is, in the end, is going to be b over b minus 1 times b to the d minus 1 over b minus 1. Okay, and so now what we can do is, now we'll take an approximation step. We're going to say, well, this part of the term, 1 over b minus 1, is small. We're going to ignore that. And what we're going to say is, if we look here approximately, n of b comma d is approximately equal to b over b minus 1 times b to the d. Okay, and so this is important here. What we see is, in general, for any given b and d, that the size of the tree, even though we're adding up, so this is really important here, we are adding up a whole bunch of terms right here, but the sum of all those terms actually asymptotically doesn't make a difference in the size of the tree. What it tells us is all of the nodes are really at the bottom of the tree, because we have the b to the d here and the b to the d there, and the number of surplus nodes we have in the other levels, it's just a factor of b over b minus 1. So with a branching factor of 2, we're going to see an overhead of 2 in the number of extra nodes you have in the tree versus the nodes that we have at the bottom layer. And as the branching factor goes up, the number of nodes in the rest of the tree gets smaller and smaller in proportion to the number of nodes that we see at the bottom. And so this makes a lot of sense, right? This is exactly what we were saying about this picture here. Obviously, most of the nodes seem to be at the very bottom there. And so that's the ones that are at the top are just a very, very small proportion compared to everything else. Okay, so this is the basic factor of what we're going to get. And that's going to allow us to start to build our algorithms based on the fact that the number of nodes that we're going to see at the bottom of the tree is going to be most of the nodes we see overall. Okay, so now we can start to think about algorithms that we want to run, algorithms that we can use to search in a tree. Okay, and what we're going to find is that there are some very, very simple algorithms we can use to traverse trees. And again, most people have probably seen this before in a graph theory course. But there's some very simple algorithms that we can use, and we're going to first look at them to see how we can start to generate these. And what we're going to start out with is we're going to start out with doing a breadth first search. Okay. So, oops, sorry, here. Algorithm 1 is going to be breadth first search. Okay, so breadth first search, again, it's going to go in breadth first order. It's going to go from the top of the tree and it's going to work its way down. And if we look at pseudocode for this algorithm, well, let me just bring up pseudocode here. We don't need to wait for me to write this down. But we have pseudocode here. So we're going to do a breadth first search. We have a from state and we have a to state. And it's going to work as follows. So we're going to push the first state onto a queue. We'll talk about that queue in a second. While the queue is not empty, then we're going to basically add the children of that state to the queue and then continue the process. Okay, so I'm going to leave this up here for just a second, and then we'll draw a small tree and we'll show what this process is. And we'll talk exactly about how this queue works. Okay, so what does a breadth first search do? So we're going to have a tree here. And for simplicity, we're going to name these A, B, C, D, E, F, G. And now we're going to imagine that we have a queue. And what we're going to be doing is we're going to, if you remember from the pseudocode, what we're going to be doing is we're going to be putting nodes onto the front. Sorry, we're going to be putting nodes onto the back and we're going to be moving them from the front. So I'm going to start by putting A at the start of the search. I'm going to put A on the back, and then I'm going to remove A from the front, and I'm going to put its successors. So a breadth first search, we have this queue, and this is exactly what you'd expect from in regular computing science. A queue sometimes is used more generally, but we're going to be adding things to the back and removing things from the front. So the first in is first out. Okay, so we added A. We're going to take A off, and then we're going to get the successors. So here we're using our successor function from the last lecture, and that's going to give us nodes B and node C as the successors there. So I'm going to put them here in that order, B and C, and I've taken A off, so we'll cross that off. Okay, so now what we're going to do is we're just going to continue to repeat this process. We take B off of the queue. We're going to generate its children, which are D and E. And so A, just to make this clear, so A was taken off first, B was taken off second. As you can see, the C is going to be third, but we'll get there in a second. Okay, so we take B, we generate its two children of D and E. We place them onto this queue. We take C off, it has two children, F and G. Put them on the back, and we continue to remove from the front, and then there's no children here, so we'll do D, E, F, and G. Okay, and just to label these 4, 5, 6, and 7. So that gives us a breadth first search, and what we can see here is that we go from the top of the tree to the bottom of the tree, and we use this queue to keep track of the order that we're going in. There are some other things that we had in the pseudocode, like you might be checking for a goal, and in practice you might also be checking for duplicates if you thought you were in a graph. But right now we're assuming that we're in a tree, so we're not going to worry about that process of looking for duplicates. Okay, so now we want to answer these questions about the complexity of this algorithm. Okay, and so we're going to look at different pieces and say, you know, what is the time that it takes to run this? So the first thing we want to know is it complete? Is it going to find a solution if one exists? And you see if there's a solution node that's inside this tree, and if there's a path to that node, then we'll clearly go through all the nodes in the entire tree. We don't drop something or get rid of anything. And so it would say, yes, this isn't a complete algorithm. The second thing we could look at is whether it's optimal. And remember, right now we're working on the assumption that all edges have the same cost. They have unit costs. And so because we're going in layers from the top of the tree to the bottom of the tree, we're going to do all of one cost before we go to the next cost, and therefore we will always find optimal solutions. The next thing we would, so it is optimal. If we think about the solution quality, we have nothing to add there except it's going to find the shortest path. And when we talk about the time complexity, now we want to know how many nodes did we expand, and also the space complexity. Except that these are both going to be the same. And it's going to depend on whether we're in a polynomial state space or an exponential state space. So in a polynomial state space, then what we're going to see is r to the d, because that's the number of states we'd have at depth d. The space would be also r to the d. Now there are some caveats to this. R to the d is the number of states that we would have in the entire state space. And so I didn't actually do the summation. And so we're going to come back to that a little bit later in the class. But so we'll look at that. In an exponential domain, then what we're going to see is the number of states is b to the d, and in both time and in space. Because inside here, when we are generating these states, we're going to have, in fact, the entire last layer will be in here at the same time. And so that'll be b to the d nodes, because we know that the last layer is the size of the entire tree. And so b to the d and b to the d for time and space, because of course we have to process all of those. Okay, so we could think about then whether we could do better or not. And it might depend on some of the properties here. For instance, if we started to think about like different edge costs or other things like that, or if we thought about whether this wasn't a tree, but maybe whether the state space had cycles in it. And so that's something we might want to analyze, but we'll get to that again later in the course. Okay, the next algorithm we're going to run here is a depth first search, which again you've probably seen before, but we're going to look at this as just a variation of the first algorithm. And what we're going to do is we're basically going to run the exact same algorithm, except now our queue that we're using is going to be it's going to be a stack. So we're going to push things in, we're going to pull them out. So the first thing that goes in is the last out, or the last thing in is the first out. Okay, so what we're going to do is we can look at this exact same problem, and we can think about just making this exact one tiny little change to how we run this algorithm. So we have our same states here, A, B, C, D, E, F, and G. And now we're going to start by putting A at the front. Okay. Actually, and what I'm going to do here, because we're going to be pulling them on and pushing them off. So here we're going to put A on. Sorry. So we're going to put A on here. We're going to choose to expand A as the first node that we expand. And as we do that, then now what we're going to do is, just like before, we're going to put the two children on. And so we'll put those on. We put C and then B here. But now what we're going to do, so I've taken A off, is instead of continuing to take from the bottom, we're now going to take from the top. So the next thing I'm going to do is I'm going to take B off, and B gets to be number 2. And when I've done that, now I'm going to get the children of B. So the children of B are D and E. And what I'm going to take off is the node that is on top here. So the third node is the node on top, which is D. D doesn't have any children, and neither does E, so that gives us a fourth node. And then we're going to continue with C here. And so if we expand C, then we're going to get G and F. And now we can write the ordering of the rest of the nodes. So that was 4, 5, 6, and 7. And so what we see is by making one change to our data structure, by the last thing in is the first out, then what that one change does is it changes a breadth first search into a depth first search. Okay. And so that works. It's going to find a solution. And now we're going to look at the complexity here. How does this work? Okay, so the first question is this algorithm going to be, actually, they say something more about implementation details here. So one thing to look at is that there are multiple ways to implement something like this. And so when we describe a depth first search this way, we can have two implementations. We basically, we make this one line change to our implementation, but this may not actually be the best implementation that we use in practice. So getting into a little bit of the practical details, very often when we implement a depth first search, what we do, especially when a single state is large, is we keep one copy of a state in memory, and then we modify that state in turn. So when we apply an operator, we undo an operator, and we only apply them to one copy of the state. And so doing something like that, when states are much larger than the operators, we might be only keeping operators in memory instead of states in memory. And things like that can be much faster in practice. Maybe there's a factor of 2 in practice if you keep one state in memory and you modify that state as opposed to making new states all the time. Again, this depends on exactly your state representation, but this is a place where the language that you choose, the ability of that language to make copies or to modify things inline, how you can pass things, whether you're running recursively or using an actual stack, all makes a big difference here. And so you need to be aware that if you were starting to implement these things, there can be a vast difference in exactly the same algorithm and the actual performance that you get based on whether, for instance, you're modifying a state in line and keeping one copy of it, or if you are keeping multiple copies. But then we can start to think, oh, but if you want to run in parallel, which we'll talk about at some point, then we have to think about that again, because you can't just modify one state when it's in parallel, because multiple threads would then be modifying a single state. So there's a lot of interesting things here when it comes to running and implementing this in practice and trying to get good performance. So let's look at our depth first search. And so the first thing we want to look at is it complete? And what we see here is if the tree is finite, then I'll be able to go over this entire tree, and eventually I will run through the entire tree and I will find the goal. And as long as it's finite, there's no cycles, that it really is just a tree, then we do have a complete search algorithm. Now, what about optimal? Okay, so optimal, it depends actually. So if you knew, for instance, that this was a tree and the goal was always going to be at the bottom of the tree, then you would be optimal. But if the goal is allowed to be anywhere in the tree, if the goal is allowed to be anywhere in the tree, actually you're still okay as long as there's only one goal in the tree. Okay, so imagine here, if I have a goal, there's only one goal and the goal's up here, well, I'm going to go up and down, and then eventually I'll come back here and get back to C and I'll be fine. The place that will get in trouble with depth first search is if I have two goals. So if both D and C are goals, then I can come down and find D as the first goal, and I might terminate at that point and not find the shallower goal that's sitting at C. Okay, now we said earlier that we assume there's one goal, so we'll just say here, yes, if there's one goal, and if there's no cycles, right? If there are not two paths to get to any node, that is, it really is a tree. Okay, well, what is the time complexity here? Okay, in the worst case, I have to traverse the entire tree. And so that's going to mean that I have to look at B to the D nodes, or here I should say O of B to the D. Or I could be theta. I mean, yeah, we can be more precise there, but we're going to be a little bit imprecise about some of these things. And now we have to ask, how much space does it require? And this is where depth first search has some properties that make it better than a breadth first search, in particular because I'm only keeping one branch at a time. And again, we're going to assume it's a tree. then in that case, what I'm going to see is that in memory, I'm only going to have like one branch and the neighbors of that branch in memory. Or I might have something like this in memory. And as I go down the tree, I'm going to be able to cut off very, very large portions of it because I'm only going to keep approximately d states in memory. So the space complexity is b times d. And so that looks okay, but we might want to try and do better here because the time complexity is the time complexity, you're not really going to be able to get past the time complexity, right? There's b to the d nodes. It could be the last one that you look at if an adversary is ordering them, and so you can't avoid that. In space, actually, it's hard to do much better there too. But really what we'd like to do is get better properties up here about this complexity. So we'd like to be both optimal and complete, and we'd like to get rid of these caveats if there's only one goal and if there's no cycles, because those aren't great caveats to have. Okay. And again, this is looking at an exponential tree. As I said, we'll start to deal with polynomial state spaces later on. Okay, so what we want is we want a better algorithm than this. And the better algorithm is going to be something that is going to be taking advantage of the fact that the tree grows exponentially. And if we can take advantage of that, then maybe we can get much better performance in practice. And so algorithm 3 we're going to get is called, algorithm 3 is depth first iterative deepening. Okay, and so depth first iterative deepening is an algorithm that was actually inspired by what was going on in game playing programs. So if you go back into the mid 80s and before, there's a lot of work on game playing programs using alpha beta search. And they would do this iterative approach where they'd search deeper and deeper into the game, and they would use the information that they got from shallower searches to be able to do better. And what actually happened is that Rich Korf is one of the early researchers in the field. He came to UCLA and visited Judea Pearl, who was also another earlier researcher in the field. They were talking about how they could put together some of the ideas that were being used in games and put them into single agent search. And they came up with this algorithm, and Korf then went and published that. And if you do look at that, though, you will find in that paper that there's an acknowledgement to Judea Pearl for his contributions to that work. Okay, and so the idea here is we're going to do a depth first search at depth. And we're basically going to say do depth 1, and then depth 2, and then depth 3. And then we're going to do this all the way until we get to D, or C star, the optimal solution cost, so that we eventually will find the goal. And if you have a sense of this, you can think about like, well, I do 1 and then 2 and then 3 and then 4. Eventually, whatever the cost of the optimal solution is, then I'm going to find that cost, and I'll do the search limited to that depth. And so intuitively, that's going to help us to be optimal if there are multiple goals present. And the other thing here that we didn't talk about, but the time complexity of a depth first search as b to the d, where d here is actually the depth of the entire tree. And so here, what we're really going to do is we're going to be limiting d as c star, which is the actual solution cost. So what you can see in a depth first search is if you have a very, very large tree, but the goal is at the very top of the tree, we could spend a very long time searching down in the left-hand branch of the tree where we find the goal very quickly in the right-hand branch of the tree. And so depth first iterative deepening is not only going to solve the problem of if there's multiple goals that I will find the right goal, but it's also going to solve the problem of maybe I'm wasting a lot of time in some branch that doesn't actually contain the goal, where the tree has gone to depth D, but maybe D and C star, the optimal solution quality, don't align with each other. Okay, and so the idea here, if we just use this tree, is we've been using here is we're going to do all of the nodes at depth 1 or depth 0, depending on how you want to count, but I think we're using 1 here. So, and then we can do all the nodes up to depth 2. And then we'll do all the nodes up to depth 3. And you would just keep doing on this process of bigger and bigger layers of search using more and more of the tree. And this may seem like, wow, you could do this, but like, aren't we going to incur a really large overhead by doing all these layers of search? And so we'll first look at the complexity. And as we look at the complexity, we'll do this calculation that is going to help us to understand the complexity of this algorithm. So what's the complexity of depth first iterative deepening? Okay, the first question, is it complete? Okay, so yes, it is complete. That is, if there's a goal, it will find it. We're assuming a constant branching factor, so whatever depth the solution is, as long as it's finite, eventually we'll increase the depth that we're doing in our iterations until we find that depth, and then we'll find the solution. So it's going to be both complete and optimal. We'll see, yes, it's also going to be optimal. Okay, so that's great, and the quality, of course, is exactly optimal there. Okay, and how much time is it going to take? So here, the time is the same as before. In the worst case, we're going to do b to the d. But here, we're going to be guaranteed that d is going to correspond with c star. I'll never go deeper than the actual solution, whereas a depth first search could go much deeper than the actual solution, and that would give us a much more expensive time complexity. Oh, sorry, but I need to justify this because we are doing these different layers here. So we'll work on justifying that in just a second. And then the space is the same as we had before, which is O of B times D. Okay, so I said here, I made this claim a second ago that the time is actually B to the D, but let's take a look at this and see why this is the case. And the question is, what is a depth first iterative deepening search doing? And so let's go back to the analysis we did before. So I want to think about a Dfid on a tree with branching factor D and depth D. Branching factor B, depth D. So what is it going to do? Well, it's going to be a summation here. And actually here we're going to start from 0. Again, 0, 1, this doesn't really matter. But we're going to go from I is equal to 0 to D. And so we're going to do iteration depth 0, depth 1, depth 2, depth 3, depth 4, depth 5, all the way up until we get to depth D. And in this case, again, D is equal to C star, the optimal solution cost. And then what we're going to ask here is, well, how many nodes we do? Well, the number of nodes we do is going to be n of b comma d. That is the number of nodes in a tree that has a branching factor b and a depth d. So we want to know, how big is this tree? And what we're going to use here is we're actually going to use our approximate solution that we got from our previous analysis, and we're going to write this out. So this tells us a Dfid, branching factor b and depth d, is equal to, and what we're going to see, remember, so this is b over b minus 1 times b to the d. So this is going to be b to the 0. Okay, and then we're going to have b over b minus 1 times b to the 1. And then eventually up here, we're going to get b over b minus 1 times b to the d minus 1, and b over b minus 1 times b to the d. Okay, and what we notice here is, the first thing we notice is there's a b over b minus 1 that we can factor out, and then I get b to the 0 plus b to the 1 plus b to the 2 plus b to the d. And what we notice here is that the inner portion of this equation right here, this is exactly what we're actually computing. This is actually exactly n of b comma d. Okay, so that's n of b comma d. Then what I can say is that this here is equal to b over b minus 1 times b over b minus 1 times b to the d. Okay, and this is equal to b over b minus 1 squared times b to the d. Okay, so assuming that the branching factor is constant, then this term right here is just a constant factor. And so this is equal to, overall, it's bounded by b to the d. Okay, so what we see here is a depth first search, although it does all these iterations in the same way that the early iterations were amortized away by the last iteration, which is so expensive. we see the same thing happens in a depth-first iterative deepening search. And so all of these extra layers here basically go away, and their cost is minimal compared to the cost at the very end of the tree. We have a slightly larger constant here, but it's not much larger. And in the end, the number of nodes we look at is b to the d, and that's how we get our term up here. Okay, so that gives us the running time of depth-first iterative deepening. And that is the first example we've seen, and we'll see other examples of where we take advantage of the fact that the state space grows exponentially. We can, the layers that we do as we're going down towards the very bottom layer of the tree, those extra layers don't really cost us anything in comparison to the last layer, and so we can amortize them away. Okay, and so now we want to ask this question, and the question is, can we do any better than this? So is this, if we have no extra information, so in the rest of the class, we're going to start asking, how can I use extra information? How can I build extra information? But up to this point, we have no extra information. So I've got uninformed search algorithm, and I have no costs in my graph. We're all unit edge costs here. So can we do any better? And it ends up, we can actually show that Dfid is both time and space optimal. That is, you cannot get an algorithm that is admissible. That means, and that means that it's going to find a solution if one exists or is complete. Admissible in this case, we're going to find an optimal solution. So this is just another term that's been used for algorithms in the past. We can't find another algorithm that is going to do better or can do asymptotically better. And so there's two things here we're going to think about of time, and the other thing we'll look at is space. So in terms of time, if we're going to claim that it is optimal, then what we would have to say is, we could ask the question, is there a better algorithm? So we think about, if I have a tree, and I'm thinking about an algorithm that's searching this tree, okay, and of course this tree could be much bigger, and I'm asking the question, is there an algorithm that's going to do better than depth-first iterative deepening search in time complexity? And what we would see is if that's going to be the case, there has to be some node here that was expanded by Dfid that was not expanded by the better algorithm. And so here, if there was some node that wasn't expanded by this other algorithm that was supposed to be faster, then all we would have to do is create a new problem instance where this node was the goal. And then this algorithm wouldn't actually be finding the optimal solution, or would be doing more work on that problem because it didn't expand it where our algorithm Dfid did. And so either case it's going to be that it's actually going to do B to the D expansions on that problem. And so there cannot be an algorithm that is better and somehow avoids some piece of work, because whatever work it avoids, we could put the goal there and then we would make the solution, the algorithm, not be complete. Okay, so that gives us that property. And now what we're using implicitly here, and it isn't always stated explicitly, but there's an implicit idea here that the state space is more or less black box. That is, I don't have access to the internals. So you could imagine, and this is what happens in planning. In planning, you could look inside a state and say, oh yes, but I knew that those states couldn't be goal states because of some other implicit information I got out of these states. But for our sake, right now, we're assuming we have no other information. And given no other information, all I have is a successor function. If I somehow chose not to expand some state here, then I could give you another problem where that was the goal, and then that would cause me not to be optimal or complete if I was never going to expand that problem, and therefore I couldn't actually do better. Okay, so that says, hey, we can't avoid expanding those states, but what about space complexity? Okay. So that was that's just a simple argument. If I could create a new problem if you didn't expand a node, where the node that wasn't expanded was the goal, and then you wouldn't be optimal. Space complexity is actually quite interesting. And space complexity here, the optimality has to do with the type of computer that we're running on. Okay, so I haven't looked at this, but maybe in a quantum computer we could make a different argument. Maybe we could do better. But if we look at sort of a classic computer here, there's a number of different models we could use, but If we look at a classic computer, then we're thinking about we think about the steps that a program runs. And in the computer we're looking at, we're going to assume that we're representing things as bits. And so for a bit, one bit basically, or bits in general, give us an exponential number of steps that we could think about, or values out of a certain number of bits. And so if we think about this, this relationship, so it says if a program runs, if we run for k steps, okay, so we've just run k steps, whatever those k steps have to be, then because we have to keep track of these steps, and those steps have to be unique, we can't repeat them, then somewhere inside the program we need log k bits of memory to keep track of the k steps that the program's running. Okay, I'll just say this again. So if we're going to have a program that runs for k steps, and we need to keep track, the minimum thing we need to keep track is a counter that says, okay, you're in step 0, step 1, step 2, step 3, all the way up to k minus 1. And the only way we can do that is by storing it in bits. And so that's going to give us log of k bits. And that says that if you're going to run for k steps, you need at least log of k bits. And so what we know is in exponential trees, we're going to run, so in an exponential problem, we run for b to the d steps. And if we're going to run b to the d steps, that means we need log of b to the d bits to run it. Okay, and log of b to the d is equal to d log b. Okay, and that's telling us, especially if b is constant, that the amount of, to run for b to the steps, you need O of d memory. Otherwise, you can't keep track of the b to the d steps, and the program would be required to repeat itself. Okay, so that says in order for any program, again, on a classical computer, to run for b to the d steps, it requires log of b to the d bits to just keep track of the program state. And that's going to require O of d memory. And we require O of d memory to do a depth first search, which is what we see up here. Space here is O of b times d. And so we see here that, and because we've assumed that b is constant, then this becomes O of d. And that says we actually cannot do better than this. So it's very interesting at this point. We see Dfid is both time and space optimal. And so for uninformed search algorithms, we're not going to be able to do better than this. Okay, so this is the end of the introductory lecture on exponential search, primarily on exponential search, and our basic algorithms here: depth first search, depth first iterative deepening, breadth first search. And there is a demo on the Moving AI website that allows us to look at these trees, allows us to run these different algorithms, and allows us to compare them and to observe exactly the types of things that we've said here. And so I encourage you to go to that webpage and take a look at those things. If you are taking the class with me, then we're going to do that in class as an in-class exercise. And so that wraps up our lecture, this part of the lecture. There will be a second part of the lecture that looks at best first search as a general way of searching that still stays in the uninformed space. So stay tuned for that.